Another classical algorithm to solve the minimal spanning tree problem is called Kruskal's algorithm, which is similar to Prime's algorithm. The Kruskal's algorithm, which applies the greedy strategy to incrementally add new edges to our final solution. A major difference between them is that in Prime's algorithm, the minimal spanning tree remains connected as a whole throughout the entire process, while in the Kruskal's algorithm, the tree is formed by merging the disjoint components together. Rather than adding vertices as in the Prime's algorithm, the Kruskal's algorithm focuses on adding edges. And furthermore, in the Kruskal's algorithm, we consider all of the edges at once, which ranked by their cost, while in the Prime's algorithm, although all of the edges are ranked by cost, but it only in a heap or priority queue, because in each iteration, we only explore the edges that are connected to the vertices that are already in the minimal spanning tree. Well, the overall idea of the Kruskal's algorithm is that we iterate through all of the edges which are ordered by their cost, and for each edge, we decide whether to add it to our final minimal spanning tree. So our decision is based on whether this new addition will help us to connect more vertices. Whether should we add a new edge in the minimal spanning tree? There are three scenarios, so let's specify it by drawing a diagram. The solid edges are the edges that have already been added to the minimal spanning tree. Well, the dashed edges are the edges that have yet to be decided. So in the first scenario, since the edge bridges the gap between the two disjoint components, so we should add the new edge. In the second scenario, because we need to connect in more dots, and since it connects to the unseen vertex, so we should also add this new edge. And in the third scenario, since all of the vertices are connected already, and it does not help us to make the current minimal spanning tree more connected, so we should not add the new edge. And plus, a more concise criterion to determine whether we should add new edges or not in a Kruskal's algorithm is that whether both ends of the edge belong to the same component. First, we add in a new edge to the least ordered edges for each well. So this loop is adding edges between the virtual vertex 0 and each house, which is index +1, which representing the cost of drilling a well for that house. The first element is the weight of the edge, which is the cost of drilling a well at a particular location. The second element is the first vertex of the edge, which is a virtual vertex with index 0, representing the source of the water. The third element is the second vertex of the edge, which is the index of the house that we're drilling a well for. Then, we add all of the existing pipes to the ordered edges list as edges. Each edge is represented as a table of three values: the weight of the edge, the starting vertex house 1, and the ending vertex house 2. And then we sort the list of edges based on the first element in each tuple, which represents the weight of the edge. So the key argument is a function that's used to determine the sort ordered. The sort ordered is determined by the edge weight, and the sort method sorts the list in place. It just modified the original list ordered edges to be sorted by edge weight. We initialize an instance of union-find class UF with n as its size. First, we initialize the data structure for union-find. So this initialize method takes an integer argument, size, which represents the number of members in the set. And we create a group list that holds the group ID for each member. The index of the member starts from 1, so the group list has the size +1 elements, and we create a rank list that holds the rank of each node for later rebalancing. The size of the rank list is also size +1. The array self group container holds the group ID for each member, where each index represents a house in this case, and the value stored at that index represents the group ID that member belongs to. The reason we start in the index from 1 instead of 0, it is because the virtual vertex, which is index 0, is added to the array. So the indices are shifted to the right by 1. We adding one more element to the container, which allow us to keep track of the virtual vertex. We input the index of a person into the find function and then return the group ID that the person belongs to. First, we check if this person is the representative of its own group by checking if self-group at person is equal to this person. If it's not, we recursively call find on the self group at person to find the representative of the group. So this step is called path comparison, which helps us to reduce the height of the tree in the union find data structure, which will improve the performance of the find operation. We define a function union to join two groups together. These two groups are represented by person 1 and person 2. First, we call the find method to find the group ID of these two persons, and if these two persons belong to the same group, we return false. That means these two persons are already in the same group, and there's no need to merge these two groups. Otherwise, we perform the union operation by attaching the group of lower rank to the group with higher rank. So how could we determine that? We just comparing the rank of each group which is stored in the rank list. If the rank of the first group is higher than the second group, then we just attach the second group to the first group. But if the rank of the first group is lower than the rank of the second group, we just attach the first group to the second group. And if the rank of the two groups is equal, we just attach the first group to the second group and increment the rank of the second group by 1. And after we perform the union operation, we just return true. We tweak the union A and B a little bit to make sure our code is more efficient and concise, but in most implementation of the union find data structure, we do not return anything for the function of the union A and B. However, in this case, we return a flag to indicate that whether the join actually happened or not within the function. So with this trick, we only need to invoke the union A and B function in our iteration, rather than we have to invoke the find A and find B to check whether they are equal in our initiation. We also initialize a variable total cost to keep track of the total cost of water supply, and at the end, we return the total cost as our result. And for each iteration, we get the age which is represented by the cost and house 1 and house 2. We then use the union method of the union find class to determine if the age should be added to the final minimum spanning tree. If the age is added, then we should also add the cost to the total cost. Let's try to analyze time complexity. Since we just applied the union find data structure in our algorithm, so let's begin by just make a statement about the time complexity of this data structure. Let's say we have k operations, either union or find method are applied to L element, so the total runtime is O of k multiplied by log of L. Well, the log is the iterative logarithm. Taking into account the path comparison and union by rank optimization, which used in implementation, the iterative logarithm function provides an upper bound for the number of times that the logarithmic operation can be applied to the elements. The time complexity for adding virtual edges to the list of edges, which costs O of n time, and then we're iterating through a list of m pipes and appending each edge to the ordered edges list, which takes O of 1 time for each iteration. So the time complexity is O of m in total, and build a list of edges which takes in total O of n plus m time. The time complexity of sorting a length n array is O of n multiplied by log of n, because sort method uses a comparison-based sorting algorithm such as quicksort or merge sort, which need to compare and rearrange the elements in an array. The number of comparison increases logarithmically with the size of the array. Hence, the time complexity of sorting the list of edges which have lengths of n plus m is O of n plus m multiplied by log of n plus m in the average case. We iterate through the sorted edges, and for each iteration, we invoke union method, which requires to process n element in at most O of log of n time. Well, log is the iterative logarithm. We perform n plus m operations union method, hence the total time complexity of all of the union find operation in this for loop is O of n plus m multiplied by log of n time. So to sum up, the overall time complexity of this algorithm is O of n plus m multiplied by log of n plus m, which is dominated by the sorting step. The union find data structure uses an array of size n plus 1 to store the group ID for each member, since the index starts from 1, and another array of size n plus 1 to store the rank of each node for later rebalancing. So the space complexity of union find data structure is O of n space. We store all of the edges, which includes n plus 1 edges, to connect the virtual vertex to n houses, and m edges to connect between the houses, and each edge requires a constant amount of space to store the edge weight and 2 endpoints. So the overall space required by the list of edges is proportional to n plus m, which is O of n plus m space. Finally, the space complexity of sorting algorithm depends on the implementation of each programming language. For example, the Python here uses a built-in list of sort method, which uses team sort algorithm, has a space complexity of O of n, well, n is the number of the elements, meaning that the memory usage scales linearly with the number of elements. So this makes it well suited for sorting large lists, as it doesn't require additional memory proportional to the size of the list. So to sum up, the overall space complexity of this algorithm is O of n plus m, which is dominated by the list of edges.